Hello, welcome to this part. So in this part, we are going to discuss how do we find out the actual depth of neutral axis and critical depth of neutral axis in case of doubly reinforced beam. So the process is similar like we have used in case of singly reinforced beam. The only addition is the parameter for the compressive steel. So first we will see how do we find out the critical depth of neutral axis, which we represent as x naught. And the depth of critical neutral axis is obtained with the same method as that for singly reinforced section. So the same formula we will use here to express to give the expression of critical neutral axis. So as you can see, you must be familiar with this diagram, as I have already used this diagram in case of singly reinforced beam. So the same diagram we can use to find out the value of x naught. So if I write here x naught as this one, and x naught is for the balanced section. So in case of balanced section, FCBC value is equivalent to sigma CBC. Similarly, FST value is equivalent to the sigma ST. So here I can replace this as sigma ST by M, and FCBC is replaced by sigma CBC, and X is replaced by X naught. Okay. So now here using the similar triangle property, so using this ratio, so I hope you are familiar with this formula. So this formula is basically dependent, based on the similar triangle property. So this triangle is similar to this triangle, this one, this triangle. So this FST value is actually this one. So this FST by M actually showing this FST by M. So by using the similar triangle property, we get this expression. So sigma CBC, so this value upon this value will be equals to this value upon this value. So the same phenomena we have used here. So this is x naught, and this will be d minus x naught. Okay. So there you can see sigma CBC. Sorry, I said wrong. The ratio of this side to this side will be equal to the ratio of this side to this side. So we can use similar triangle property in many ways, like the ratio of this side to this side, or equals to ratio of this side to this side, or in other way what we can do is the ratio of this to this will be equals to the ratio of this side to this side. Okay, so this time we have used this one. So the same formula I have already discussed in case of singly reinforced beam. So if you have any doubt, if you are not clear with this formula, you can refer to those lectures, because this actually is the extension of that part. So as I have written here also, which is the same as that for singly reinforced beam. Okay, so in the same manner we can calculate x naught value for doubly reinforced beam also. Now the major point is how do we find out the actual depth of neutral axis. So actual depth of neutral axis is actually dependent on the amount of compressive steel also. So now actual neutral axis will also be I will also use the same formula. The only extension there will be the provision of compressive steel. So to calculate the value of actual neutral axis, so as I written here, the actual neutral axis of doubly reinforced beam is calculated by taking the moment of the tension and compression area above the neutral axis. So the same the same concept we have used in singly reinforced beam also. So we used to calculate x value by equating two parameters: moment of the tension area equals to moment in the compression area. So the same formula we are using here, moment of compression area about neutral axis to the moment of tension area about neutral axis. So first I will show you the diagram. So in this diagram you can see this is the neutral axis. So above neutral axis there are two areas. One area is this one, and the second area is this one and this one. So if we add both of this area, this will become m dash minus 1 into ASC. Okay, so above neutral axis there are two compression area, while in case of singly reinforced beam there was only one area. So that is the only change in this formula. So first of all we will try to find out moment of compression area. Well, what is moment of compression area? Like we used to find out moment of force. If we find out moment of force, so moment of force is force into perpendicular distance, and this perpendicular distance is between the axis about which we are finding the moment and the point where force is applied. Okay, so on the same line we find out moment of area also. So here moment of compression area. So compression area is this one B, and this value is X. Okay, and this one, the center, you can see there I have already I have provided another parameter also, d dash. Well, d dash is the, like we used to have effective cover in the tension zone, d dash is actually effective cover in the compression zone, because we are providing reinforcement in compression zone also. So the center, so from the center of this bar to the topmost line, it will be d dash. So we will use this d dash parameter later also, but first we will find out moment of compression area. So moment of compression area will be the sum of moment of area of this part and moment of area of this part and this part. So how do we do that? So this is the formula that we generally use. So first of all, in this case, what we are doing is uh, the whole part we are taking here as b into x. Sorry. So here I will write here the relation. So moment of compression area in this case will be uh, moment of concrete area above neutral axis, excluding the area of compressive steel. So this becomes the moment of area for the concrete. Now, as the steel in the compression, we have replaced it by the equivalent area of concrete. So I will add here plus moment of equivalent area of concrete okay. So moment of equivalent area of concrete in compression zone. So in the singly reinforced beam, what we used to do is we used to take this much part only. But in case of doubly reinforced beam, as the compressive steel is there, so now in this case we are taking this part also. So now both of these part I have written in formula. So I will show you this in the form of formula now. So first I will write this as A part and this is as B part, and then I will distinguish this as in the formula also. So this is the formula. So in this formula, this part is the A part and this part is the B part. Now A part is moment of moment of area of the concrete excluding the area of compressive steel. So there you can see moment of area of concrete. So Bx, so I am x expanding this as B into X by 2. So this becomes, sorry, this becomes area of concrete, and this is the perpendicular distance. So I am now writing this here, B, and this one is X. So this becomes Bx. Bx is the area of this concrete, okay, and where this area will concentrate, obviously where the diagonal will meet, this point. So distance between this and this will be the perpendicular distance, which is x by 2. So this is how this bx square by 2 will come. Now minus, as I said, that this will be excluding the compressive area of steel. So in this case, what we are doing is, now we are excluding, we are deducting the area of steel in compression. So the whole moment of area for the compressive steel we are actually deducting. So for example, there must be the steel. So their moment of area will become ASC. ASC is the area of this steel, and the CG of this steel will be at the center. So from this CG and to the topmost point, this is actually the D dash. Okay. So distance between neutral axis and their CG will be x minus D dash. So here now I am writing as ASC as the area of steel in compression multiplied by the perpendicular distance, and perpendicular distance is basically between the CG point of reinforcement and the neutral axis, so which becomes x minus D dash. Now this becomes the A part. Now as I said that this steel is now replaced by the equivalent area of the concrete. So what we are doing is, now we are adding the moment of area of this equivalent area of concrete. So in this case, now we are adding the B part, which is 1.5 times of M into ASC. So this is the equivalent area of the concrete. This one is the equivalent area of the concrete. This and this one, and multiplied by the perpendicular distance. So as the equivalent area of concrete is also placed at the same level of the steel, so the distance between its CG and the neutral axis will also the same, which is x minus D dash. So this is how this formula is being evolved. So by further elaborating, now in this case what we can do is ASC bracket x minus D dash, we can take this common, and by taking this common we can write this value as bx square plus bracket 1.5 times of m minus 1 into ASC into x minus D dash. So this is how the formula of moment of area above neutral axis is calculated. So this is one part. Now we will find out moment of tensile area about neutral axis. Well, it will be same as in case of singly reinforced beam. So there will be no such issue of understanding. So there you can see I have used the same formula. So this is the area of steel. So there you can see this is the area of steel, and the CG of this area of steel will be here, and distance from here to here it will be D minus X. So this is the same I have used. So this M into AST is the equivalent area of concrete in place of tension steel multiplied by the perpendicular distance. So this distance is basically the CG, distance between CG of this equivalent area and the neutral axis. So this becomes the moment of tensile area. So now to calculate the value of actual depth of neutral axis X, what we will do is we will equate. So both of these equations that we have find out in the previous slide, so now we will equate them. So now you can see this is moment of area in compression and this is moment of area in tension. So by equating them, what we can do is we can find out this X value, and this X is actual depth of neutral axis. So I hope this is clear to you. So we will discuss, we will continue our discussion in the next part. Thank you.